Inside the dark, silent vault of the human skull lies the most complex processing engine in the known universe. 86 billion neurons. 100 trillion synaptic connections. Every memory, every human emotion, every mathematical breakthrough, and every spoken word originates here, firing as microscopic electrical impulses at over 200 miles per hour. For the entirety of human history, this biological matrix was tracked. It was an isolated system, completely dependent on biological limbs and vocal cords to interact with the outside world. When the body failed, the mind became a prisoner in its own bone casing. But a profound engineering threshold has just been crossed. We are no longer simply observing the brain from the outside. We are piercing the biological veil. We are translating the chaotic electrical storms of human thought into the binary logic of digital silicon. We are entering the era of the brain-computer interface. And the evolutionary trajectory of our species is about to irreversibly change. The pursuit of reading the mind began not with computers, but with a fundamental realization about human biology: we are electric machines. Centuries ago, scientists discovered that the nervous system operates through bioelectricity. When you move your hand, the tiny electrical voltage travels from your motor cortex, down your spinal cord, and into your muscles. In 1924, a German psychiatrist named Hans Berger decided to listen to this internal electrical storm. He attached crude silver wires to the scalp of a patient and connected them to a sensitive galvanometer. For the first time, human brain waves were recorded on paper. Berger had invented the electroencephalogram, or EEG. He proved that the brain's electrical output could be detected entirely from the outside. For decades, EEG remained the standard. But as engineers began dreaming of connecting the brain directly to computers, they encountered a massive physical obstacle. The human skull is a brilliant evolutionary defense mechanism. It is thick bone, surrounded by fluid, wrapped in skin and hair. Trying to read individual thoughts using an EEG cap on the outside of the skull is like trying to understand a single conversation inside a massive stadium while standing out in the parking lot. You can hear the collective roar of the crowd when a goal is scored, which represents states like sleeping, waking, or intense focus. But you cannot isolate the precise, high-frequency signals of a single neuron firing. To achieve true control, to allow a human mind to pilot a robotic arm or type on a screen, engineers realized they had to get inside the stadium. They had to cross the blood-brain barrier. They had to physically touch the cortex. This transition marked the birth of invasive neural engineering, and it immediately collided with the aggressive defenses of the human immune system. The brain does not welcome foreign objects. When early researchers inserted metallic microelectrodes into the cortical tissue, the brain recognized the invasion. Within weeks, immune cells called astrocytes swarmed the electrodes, encasing them in dense scar tissue. The electrical signals slowly faded into silence. The interface went blind. To build a machine that could survive inside the mind, materials science had to completely reinvent itself. The first major breakthrough was the Utah array. It is a rigid silicon grid smaller than a fingernail, studded with 100 microscopic conductive spikes. Pushed directly into the motor cortex, it successfully recorded the firing of individual neurons. For years, the Utah array was the gold standard, allowing paralyzed patients to slowly move computer cursors just by imagining the movement of their hands. But the Utah array was rigid, and the brain is soft, pulsing gently with every heartbeat. Over time, this mechanical mismatch caused microscopic damage. Engineering required a radical new approach. The solution was flexibility. Today, advanced biocompatible polymers are being spun into electrode threads incredibly thin, thinner than a human hair and softer than the neural tissue itself. Because human hands are far too clumsy to insert these microscopic filaments without tearing delicate blood vessels, engineers had to build automated surgical robots. These precision machines use advanced optical mapping to avoid veins, rapidly sewing thousands of electrodes into the brain with micrometer accuracy. Yet, another team of engineers looked at the violence of opening the skull and asked a completely different question. What if we use the highways already built into the human body? This led to the creation of endovascular neural interfaces. Instead of drilling through bone, doctors insert a tiny, flexible metal mesh called a stent rod into the jugular vein in the neck. Using a catheter, they guide this sensor up through the circulatory system until it rests in a blood vessel directly adjacent to the brain's motor cortex. The interface reads the brain's electrical commands through the blood vessel wall, completely bypassing open brain surgery. We had finally found multiple ways to capture the signal. But raw electrical data from 86 billion neurons is just chaotic noise. We needed a translator. Capturing a microvolt spike from a neuron is a hardware problem. Understanding what that spike actually means is the greatest software challenge in human history. When you imagine moving your arm, your brain does not send a simple line of code. It fires a complex, distributed pattern across thousands of neurons. Furthermore, no two human brains are identical. The exact electrical symphony that represents the word hello in one person's brain looks entirely different in another's. This is where brain-computer interfaces merged with artificial intelligence. Advanced machine learning algorithms now act as the ultimate translation layer. In clinical trials, a patient sits in front of a screen and is asked to imagine moving their hand to the right. The AI records the specific electrical firing pattern that occurs in that exact moment. It repeats this process thousands of times. Through deep learning neural networks, the computer builds a custom dictionary of the user's mind. The results have broken the boundaries of medical science. Patients suffering from late-stage ALS, completely locked inside unresponsive bodies, are now typing at conversational speeds. The AI is not just looking for hand movements anymore. It is decoding the complex signals intended for the vocal cords, the lips, and the jaw. It reads the intent to speak, translates the raw neurological data into text, and uses a synthesized voice to speak the patient's thoughts aloud in real time. But this technology is not just moving outward, it is becoming a two-way street. Modern bionic limbs are now being equipped with tactile sensors. When a robotic finger touches a glass of water, computer translates that pressure into a tiny electrical pulse and sends it back into the sensory cortex of the brain. The patient does not just see the robotic hand touch the glass, they physically feel the object. The boundary between biological flesh and engineered machine is officially dissolving. While restoring lost medical function is the immediate priority, The long-term reality of brain-computer interfaces extends far beyond healing. We are rapidly approaching the threshold of human cognitive augmentation. Currently, the speed at which humans can output information is physically limited by the speed of our thumbs on a screen or our fingers on a keyboard. Our brains can process complex realities instantly, but we communicate them at a crawl. A high-bandwidth neural interface removes the physical bottleneck entirely. Imagine the implications across professional landscapes. For a project manager in the IT and software development sector, managing complex system architectures and delegating team resources could shift from typing on a keyboard to instantly projecting structural intent directly into a cloud network. Complex code structures, vast databases, and systemic frameworks could be visualized, manipulated, and compiled at the absolute speed of thought. The human mind would interact with digital infrastructure as naturally as it moves a biological arm. This evolution brings us to the concept of synthetic telepathy. If a brain can output data to a computer, and a computer can input data back into a brain, then two isolated human minds can theoretically connect through a digital network. Humans could share raw spatial concepts, complex emotions, and intricate ideas instantly, without ever speaking a single word. It would be a fundamental shift in how human empathy and collaboration function, creating a localized hive mind of shared experience. Yet, as we open the ultimate biological vault, we face a terrifying new frontier of security. If a machine can read your intent, who owns the data of your subconscious? If a system can write sensory feedback into your cortex, can a malicious architecture manipulate what you see, feel, or believe? The privacy of the human mind has always been absolute. No matter what happened in the physical world, your inner thoughts remained entirely yours. As neural interfaces integrate with global digital networks, the battle for cognitive liberty and neuroprivacy will become the most critical human rights issue of the 21st century. We are leaving the era of pure biological evolution. By fusing our nervous system with artificial intelligence, we are rewriting the definition of human capability. The skull is no longer a barrier. The mind is now online. And the universe of thought is finally preparing to speak directly to the machine.